Well, let me talk about one of the most important and critical assumptions in autoregression models, the proportional odds assumption. The proportional odds assumption, which supposedly should hold in the proportional odds model, the prototypical and the most commonly used autoregression model in empirical research. So let's begin with an equation that we already derived in one of my previous lectures. So the probability y equal to a response level given x is equal to the difference in two cumulative density functions. So let's say if the error term in the structural model for y star follows a standard logistic distribution, then the cumulative density function going to be a standard logistic cumulative density function. And the difference is going to be the difference in the two cumulative density function of the standard logistic distribution. Okay? And here I have a question for you to think about. Well, we just talked about equation for the probability y equal to m. How about the probability for y smaller equal to a response level? So it's not equal, only equal, but smaller equal to. Okay, and given data and population parameters. Okay, and here, without further ado, it's pretty clear that the probability y smaller equal to 3 is equal to the sum of the probability y equal to 3, the probability y equal to 2, and the probability y equal to 1, since y is a discrete random variable and only takes some values, let's say from 3 to m. Okay, so here is to 3. And as I just specified, right, the probability for y equal to m is equal to this equation, right? So the probability for y equal to 3 is the difference of this two, and the probability y equal to 2 is difference of this two, and the probability y equal to 1 is equal to the difference of these two cumulative density function. And it's not hard to find that we have quite a few cancellations, right? This term and this term cancel out. This term and this term cancel out. And this term turns out to be 0. Why? Because tau 0 is usually set to a negative infinity in empirical research, right? Usually, we don't say there's a tau 0. We usually begin with the first response level of the ordered response variable, right? But implicitly, we have a tau 0 that's set to be negative infinity. And then the cumulative density function of a infinity minus a finite number, that's going to be what? 0. So this term is 0. So what is equal to? Well, the probability y smaller equal to 3 turns out to be this term only. And to generalize our derivation here, we can have this term, right? The probability y smaller equal to m is equal to a cumulative density function f and tau m minus x beta. And if we use the standard logistic distribution for the error term, we're going to have lambda, right? And we should use lambda here because it is the right cumulative density function for the proportional odds model. Okay? So the proportional odds model has an error term in the latent variable structural equation that follows a standard logistic distribution. And if this holds, then the lambda is equal to that. Okay? Simply by definition, this is just a cumulative density function of a standard logistic distribution. So for any term in the middle, Okay, we're gonna, apply these functions. Okay, apply these functions. Okay, and from here, this equation here, we can get this equation. So the probability is equal to the exponential over 1 plus the exponential. And how to solve for tau m minus x beta? Well, you follow through basic and algebraic arrangements, right? And you can get this one. And people might want to ask, what is the probability y greater than m? Well, that term is what? Is 1 minus the probability, what? Y smaller or equal to m. And you can try deriving the second line from this line. You can try that out. Remember that natural log function is the inverse function of what? Natural exponential function. So let's continue. So we're here, right? And this term, if we define this term to be odds, the probability, the ratio of the probability over 1 minus the probability, right? I just showed you that this term is 1 minus the probability in the numerator, right? In the numerator. So from here, odds equal to probability over 1 minus the probability. And if we take log of this two, if we take log of the odds, right, we can get tau m minus x beta, from here. Okay, then what we're going to do, we're going to take exponential of both sides. Since exponential function is inverse of log, they cancel out, right? And this log is canceled out by exponential. But what's on the right becomes the exponential of tau m minus x beta. So now the odds, which is equal to the probability over 1 minus probability, right? And here, 1 minus the probability is, the probability y greater than m. It becomes this term, right? And let's continue. This is known as the proportional odds model. Why? Because if we take a ratio of 2 odds here, it turns out to be the exponential of, in the big bracket, negative difference of 2 x vectors multiplied by beta. In essence, what is the proportional odds assumption? Well, it only applies for the ordered logit model. And here, to be very precise, actually it's called, cumulative logit model. There are multiple terms floating around for the proportional odds model and proportional odds assumption. Okay, and the proportional odds assumption basically says, well, for this cumulative ordered logit model, the beta stays the same. Okay, the beta stays the same. It doesn't matter which tau you're talking about. A cut point equation later on we will talk about. The beta stays the same. Okay, and once the beta stays the same, the ratio of 2 odds is proportional to each other. Okay, by a factor of, e raised to the power of negative the difference between 2 x vectors and multiplied by beta, and that beta stays constant. So this is called the proportional odds model and proportional odds assumption. When I translate this assumption into some graph, okay, some graph here, okay, so this is when the assumption holds, that is, the beta coefficient coefficient vector stays the same. And here is the probability, and all the curves are cumulative probability curves. You can see that there is a what? Parallel shift across this cumulative probabilities, right? And here's the probability y smaller or equal to 1. Here's the probability y smaller or equal to 2. Here's the probability y smaller or equal to 3, right? Different curves here, right? And they're parallel to each other, okay? They're parallel to each other, as opposed to a scenario in which this assumption violated. That is, for different threshold, and we have a different beta. So these two actually, they follow the proportional odds assumption. But for this one, we can see that, well, obviously, there's no parallel shift. This is kind of pretty curved shift as opposed to the first two, right? The first two, there's a parallel shift. But for this one, no, because its beta is different. So that's the violation of proportional odds assumption. And in terms of violation of this assumption, statisticians have devised a battery, a variety of models to address this issue. And I'm going to cover in future sessions.